particular to Tommaso that gave me this opportunity to come here and presenting not only my results, but also the opportunity to discuss with many of you for collecting a lot of nice ideas for working on interesting things. So thank you. Yes, in this moment, I'm working at the mathematical department in Johannesburg. And NRF and University of Johannesburg in this moment are the institution that provides some funds for me. I don't want to say a lot of things about quasicrystal, and in particular about quantum quasicrystal. I would like just to show you a few things. And I would like to start talking about clustering, which is a very general aspect. And if you have a potential that display a soft shoulder-like shape, and as the Fourier transform that at short distance has a negative value, in order to have a minimum that create a modulation, you can have a cluster phase, okay? And this it's quite general for a lot of physics. In particular, there is a lot of literature in soft condensed matter and in structure like colloidal particle solution polymer chains. Some time ago with Tommaso and Thomas Pauli in Dresden, we work a lot about Rydberg blockade regime and soft core bosons in order to observe the phase that is called supersolidity. Here is a nice example where supersolidity is present in trap, and it interacts with vortex, so the trap is under rotations. And in this institute, I have to say thanks also to Christina that showed me that also there are bubble crystal using electron in high degenerate Landau level. So thank you very much for introducing also this part of literature that is really important and makes the idea of clustering phases even more general, from classical to quantum phases. Okay, let me start from a soft matter work, in particular a PRL of 2014 by Barkan and Lifshitz, where they want to study classical quasicrystal cluster. And this start from a set of potential that are used for this colloidal structure, and in particular it's are just Gaussian minimized by this Bessel function, common Bessel function, but everything is as I said before in the Fourier transform of this potential, because they have two minima. The first one fixed for convenience in 1, and the second can generate an n-fold symmetry with this simple cos dependency. This is quite well known in the field of pattern formation, in particular using this Schwiz-Hohenberg equation. So they are able to find symmetries and cluster with different shapes. So what's happened, just another slides about this work, what's happened in some part of the phase diagram, moving the density and the temperature, they see the transition from liquid to cluster crystal like stripe, 4-fold symmetry, 6-fold symmetry, 10-fold, and 12-fold symmetry. And okay, in this field, there is also a discussion about what's happening at low temperature with all these symmetries. So, but apart from that, I'll show you something later when I will introduce the quantum fluctuation. But the problem is, as Ulrich showed to us today, these two guys are cluster quasicrystal. Okay, so this is something that in solid state was quite low, but this is something that is a quasicrystal. So let me repeat quickly with 2 slides the meaning of quasicrystal. So I took some nice picture from Wikipedia. This is simply silver depositing on aluminium, on an aluminium alloy. That is, it's quite interesting. And of course, usually in crystallography, as we have seen today, we can have 1, 2, 3, 4, up to 6-fold symmetry, although 5 and 7-fold and higher are completely forbidden. Okay, and this was believed that was true up to the day when Sheckman and all observed an icosahedral single grain that has a 5-fold symmetry. Okay, and so we have to deal with a quasicrystal. In the momentum, the main input is that the radio distance between the central spot and the other is a Fibonacci number, is not an integer. So this idea has been seen today. And then in solid matter, we have a crystal, amorphous crystal, or quasicrystal. Okay, but the main point here is that a quasicrystal structure lose completely the periodicity. We have to talk about quasi-periodicity, okay? And it's still an open problem. Recently, there are interesting work on multi-length scale potential, and then there are a lot of people that in soft matter are continuing to study this kind of quasicrystal structure. Okay. I start because I'm mainly doing Monte Carlo. So the first idea is I take quite a large number of particles, about 4,000, and with a simple classical Monte Carlo simulation, I'm able to reproduce the structure that I showed you before by Barker and Lifshitz, that were using I don't remember the method, but wasn't a Monte Carlo. Anyway. With Monte Carlo, I'm able to reproduce this quasicrystal 12-fold structure. And now, let's put the quantum fluctuation into the game. So simply, together with the potential that I showed you before, I want to add the kinetic part to my simple Hamiltonian. Okay? And I don't have a single particle anymore, but I have to go through the path integral formulation of quantum mechanics and realize that I can map this in d+1 dimension, as you might know. The main question is adding quantum fluctuation at finite temperature. What is the response of my path integral Monte Carlo? Okay, path integral Monte Carlo is not a black box. Let me give you some slides about path integral together with the Worm argument that it's quite very much important for sampling the quantum properties of a boson system. So in principle, the path integral Monte Carlo as a macroscopic Hamiltonian as only input is unbiased. There are no a priori other assumption, and I'm thinking about trial wave function for methods that are used at t equal to 0. So it's quite safe from this ill problem, and it's in principle numerically exact for Bose system. What's happened? It's extremely simple. In this case, I have my 2-dimensional off-lattice bosons with a simple Hamiltonian. I try to setting this system in order to calculate using quantum Monte Carlo energy, superfluidity, condensation, and structural property. I would like to say that this is the only method that is able to quantify superfluid fraction and condensation. Okay. What means G sector and Z sector? Essentially, my partition function is a huge integral that is in complex space. There are all these word lines that represent the quantum fluctuation of my particles. And then I have to be able to sample. So Monte Carlo enter only here, okay? The theory is very well known, thanks mainly to Feynman. And the main idea here, okay, I want to sample, as I said, superfluidity and condensation. This is done entering in a so-called G sector. That means that I have to sample not only the partition function, but also the Matsubara grid function at t different from 0. Okay, I have the time ordering operator, and then I have my creation and annihilation operator that represent my creation and annihilation of my bosons. And this is simply a geometrical sampling. So I have my worm, exactly a worm, with tail, with a tail psi and the head psi dagger. And in this way, I'm able to calculate perfectly all these quantum properties doing a simple classical Monte Carlo. So in my complex space, I can redraw my word lines, I can open my word lines, and I can insert for the grand canonical ensemble, for instance. And most important, I can swap the word line between themselves. That means that I can to study permutation. I'm introducing the Bose-Einstein statistics in this regime. Okay, this mainly is the tool that I need for studying my quantum quasicrystal. Okay, some test. I start slowing increase lambda, and for few thousand particles, I need a large amount of particle because a quasicrystal structure needs quite a big amount of particle to be recognized. So, and here I show some snapshot of my simulation, showing also the radial distribution function. Each spot here is a word line mapped on a XY plane. So I should be able to see the delocalization of my particle throughout the free space. Okay, I'm able to see quite nicely a fourfold symmetry and also the two quasicrystals. That seems quite stable. Okay, just increasing a bit the lambda, which is connected to quantum fluctuation, I can see the formation of my quasicrystal with this G of R that show this asymmetry in here. Okay, so now let's see higher size, about 4,000, using exactly the same parameter in temperature given by Barkan et al. And I see again that the structure introducing a quantum fluctuation remains stable. And but the important thing, this comes from the discussion with Primoz Zeller, that is the guy that knows in this collaboration very well the idea of quantum crystal in soft matter, recognize exactly that this is a quasicrystal because we can see these 12-fold wheels here, and at the same time, it can show overlapping between this wheel. This is the footprint of a quasicrystal structure. Here, in the Fourier space, you should recognize 12 points. I'm sorry, I try to do my best with Python, but I'm not able to. But here there are 12 points that are strictly connected to the symmetry of a quasicrystal. Okay, so at this lambda, the structure remain constant, remain as a quasicrystal. So let me go now through the temperature. Okay, in the region analyzed by the article that I showed you before, the quasicrystal remains stable, but at finite temperature, I have a transition between liquid and quasicrystal structure, although the energy at very low temperature is stabilized into a triangular crystal. So this, using our simulation, seems quite clear. Okay, the quasicrystal seems to appear only at finite temperature in this case. Okay, now I want to discuss some real quantum properties, and I want to show you the concept of permutation. Okay, you know very well the permutation in a bosonic system, although let me say that mainly in the quantum Monte Carlo, I'm sampling the density matrix, okay, which is a density matrix connected to a Bose. So this means that at the border of my beta simulation, okay, the eigenstate of the system at beta and 0 have to be periodic, but among them particles start to permute. For instance, a particle that starts at complex time 0 can permute with a particle 2, 3, 4, and this, for instance, is a 4-particle cycle. Okay? This is really important for us because it's telling us if particles are really like bosons. And this is what's happened in the core and just outside the core of our wheels that I always showing now. And I have permutation cycle that goes from 2 to 25 and sometimes even 30 particles. That is just in this ring. Now, another important quantum properties, of course, the superfluidity, that here is evaluated with the method, the first method proposed by Sepperli, that is the estimation of the area that all particles connected together can form. And the superfluidity, if we put the system under rotation with respect to the z-axis, because we are in 2 dimensions, we can have that the estimator, it's simply this area, okay? And for instance, if you consider a 2-dimensional system for studying the Kosterlitz-Taules transition, at Kosterlitz-Taules, you have this huge loop that covers all the space that you are considering. At higher temperature, this loops become smaller and smaller. It means that the superfluidity simply goes to 0. Okay? In this quite big system for a quantum Monte Carlo simulation, the superfluidity fraction that we are able to detect is about 5%. So it means that inside this structure, there is a superfluidity that is different from 0. Okay? Another important property is the local superfluid fraction. You can take this area, okay, again, map on the perpendicular axis on which you are rotating your Hamiltonian, your system, and you simply do a sort of histogram in the position d of r in order to calculate this radial superfluidity. Okay? In this way, you can see that the superfluidity is finite inside the ring and even outside. So this wheel ends more or less here. You see, it means that this wheel of your 12-fold symmetry is superfluid. Okay? And then this signal decreases. It's quite a difficult function to study, but it's, I was quite surprised that after a long time, I can distinguish quite well this oscillation of my local superfluidity. Okay, it means that the system, it is superfluid. Okay. Okay, let me move now to another point, and that what's happened if I change lambda. So far, I just keep fixed lambda. I show you the temperature behavior. What's happened if I increase the quantum fluctuation? You can see that G of R as in this black, the quasi-crystal structure that I showed you before. But if I increase just a bit further lambda, I see a clear modulation that changes completely the structure of the system. It means that quantum fluctuation are changing the structure, okay, from a 12-fold symmetry to a 6-fold. And this is quite surprising. Is a first-order transition, because it's a structural transition, and then moving further, increasing further lambda, sorry, we are going from a cluster crystal to a super solid, and then here we see the behavior of a liquid that is going to be superfluid. Let me show you some configuration that explain better this G of R, because maybe it can be quite messy, all these curves on the top. And this, it seems more clear, because moving lambda, I'm going to a crystal structure. There is a change of introducing quantum fluctuation, okay? Then I'm going to a supersolid phase. A supersolid phase is there are two different order parameters that they mix together, the crystal order and the gauge symmetry. So it means that in this case we have crystal structure, but we have also a superfluid phase that it's different from zero throughout the whole system. And then moving further lambda, we have a normal uniform superfluid. Okay. Again, I'll show you the permutation. The permutation in the crystal structure that is modified by quantum fluctuation tells us that the permutation remain confined in this droplet. Okay, I have bosons that just permute in the single site, and then again the supersolid phase has a long permutation cycle, more than 1,500 particles, and superfluidity is between 0 and 1, like before. This was proved by an old theorem of Leggett in 1975. If you have a lowering of your structure, the superfluidity will never be 1. Okay, this is something I can give you the reference. It's quite straightforward argument. Okay, I want to conclude giving you a final discussion. So today, let me assume that this phase diagram, even though, of course, I just analyzed this part of the phase diagram, and in our opinion, we have to do simulation, but this is the cluster crystal that overlap with the superfluid phase increasing lambda in order to have supersolid phase, and we have a little part of the phase diagram that show quasi-crystal phases. This physics is, I think, is really interesting. So this is the main message of the talk, of course, although there are other important examples where introducing a quantum fluctuation can generate stabilization of crystal. This is a work that we have done some time ago with Thomas Paul and Massimo Boninsegni, and we can see that for Rydberg atoms, these soft core bosons, the introduction of quantum fluctuation stabilize at higher temperature the crystal structure against the classical simulation one. Okay, so with boson statistics, I have classical quasi-classical crystal at higher temperature. But doing the only simple classical simulation without considering Bose-Einstein statistics, this transition is lowering. Okay, this is a really interesting effect. And there are also something to say about helium-4, considering quantum simulation introducing a Bose statistics versus classical simulation. But I think that everything is very well explained in this PRF 2012. So I'll stop here, and I thank you very much for your kind attention.
Questions?
I'm still trying to understand this transition from the quasi-crystal to the cluster crystal when you increase quantum fluctuations a little bit more. I mean, one big